Mm-hmm. All right. Yeah. 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 Sir. Yeah. Yeah. All right. So, hello guys, and thank you for being here for my sort of a discussion type lecture on introduction to cosmology. So, in this, we don't actually go too much into the technicalities and other like too much intrinsic details. We just look at stuff, through the to beginner's perspective, and we'll just get to know like a lot of the stuff and what's happening in the field of cosmology. So, what is cosmology? Cosmology is study of universe and the objects that are present in the space or the universe around us. So, we try to understand what they are and what is happening with the space itself. So, we have many objects such as galaxies, stars, collection of stars. You have galaxy clusters, you have superclusters, you have black holes and all other varieties and strange and many other types of objects that are still undiscovered by humanity as such. So our universe consists only of 95% of matter, and the rest is all dark energy and dark matter. So that is the in this 5%. This 5% is what we'll be dealing in this. The 5% matters what we'll be dealing in this part of the lecture, and we'll look at what are all the various kind of stuff that is present and what are the phenomena and the kind of properties of the objects that are present in the universe. So the as you know, like as humankind it was evolving. We started to explore the stuff around us. So we had literally no idea where we came from or where we are from and where we'll be going in our path and as time went on in our stay in this universe. So our ancestors, they were, like they were trying to find out ways in which they could figure out what was happening. It's like why this is happening and why is like why the sun rises in the east and why the sun sets in the west. Like basic, the stuff was kind of intrigued our ancestors. So the kind of that was a kind of the place where it all started, right? Like our inquisitiveness, our curiosity to know what's happening around us. So this is one of the illustrations by painting by Paul Gauguin, which is actually called this thing is called as what are we, where do we come from, and where we are going. So you can see people looking into the sky and understanding what are the various kind of things that is happening around them, and trying to make sense of what is happening. And these kind of observations also helped increasing their survival through the history or through the passage of time. Like we use these kind of things to this kind of thing like the position of a star as a north star. We use it to determine directions and to also like so in order to move as they were all wanderers as well before they started settling. So this was kind of the inspiration. Like we got this is the place where people started to think about uh, what the thing around them is as such. And as we know, our universe is not small. It's not small, so it is very big. So we are just like how Carl Sagan said, we are just a pale. Our Earth is just a pale blue dot in in all of the cosmos. So in such a scale, our usual metric system doesn't actually work. Like it is very tedious and it is very uh, not efficient enough to work with the normal metric system that we use for the calculations to determine stuff that is going on around us every day. So we use certain specified units that are have a large help us to observe things that are of large distances and large quantities and stuff. So one of this thing is 1 light year, which we already know. So that is basically the distance that is traveled by light in 1 year. So that is 9.461 to the power 15 meters. So this is one. So when we are measuring galaxies or say any other planet or stars, we tell them that it's just 3 light years away or 4 light years away. That means the light from that object will reach us after 4 years. So that is what actually means, and that this is the kind of kind of basis that we use for our calculation system for the universe. And we also use one astronomical unit or 1 AU. So this is basically the distance from Earth to Sun. So since we know the exact distance from Earth to Sun in our solar system, we can also use this specified fixed distance to find the other distance to other objects in relative to this. So we say probably like like how we use light years, we also use like astronomical units to also specify that. And one parsec, yeah, so parsec, so we probably have learned in our like in our first year, second years of college that uh, there is an angular way to measure the distances, angular distance we heard. So in that case, 1 parsecond can be defined as the distance from the observer to the object that makes one arc angle to that this 1 degree arc angle to the specified object. So that is that it can be like measured through the parallax thing, and then like we can measure like how many degrees does it make. So 1 parsec is the distance that makes one arc angle with the specified object from the observer. So we use like mostly we use parsec for like very great distances, since our astronomical unit is also only in the scales of 10 to the power 11 meters. So we also end up using parseconds to measure the distances to many to different galaxies and other very far away objects from us. And the one MO, that is one solar mass. So we can't like tell that the sun is 2 million or some to 200 to 20 million kilograms. That won't be like proper in terms of scientific notations when you're trying to represent the quantities in the scale of the universe. So we use a relative term known as solar mass. So this is basically the solar mass as such, which is this is the mass of our sun. So we try to measure the other stars and other objects in the universe in terms of solar mass, so that it can easy you can simplify our calculations and can be used as a good reference to solve difficult calculations. So these are some of the metric system, like the sort of units that we use in order to measure the objects that are very far or very huge compared to us. So any doubts still here or any clarifications that you have, like up to this point, you can ask. It's basically sort of a discussion, since it's a really interesting topic, and obviously there will be many doubts in many guys. So any doubts or any clarifications that you want, or anything that you would like to add on here, the room's open. All right, so I think I'll carry on. So this brings us to the next one. In this fundamental observations section, we'll try to look like there are various phenomena that like how you have gravitational lensing. So during solar eclipses or solar eclipses, you see that the light from some a path like bends. That's what due to gravity. So that's what Einstein had measured. So these kind of observations that we've seen have made us like to understand better about the nature of the universe, right? So in this section, we'll try to understand through observation uh, in the early cosmological period. I mean, the early period where cosmology was, people were able to observe the cosmos with the development in the optical technology in terms of telescopes and such. So in this like people this way that we see about how people like were able to make like good like able to come to conclusions like about the stuff that the universe is all about the nature of the universe. So one such idea which led to this is called as the Olbers paradox. So we know that during the we take it for granted that the day is basically like full of light, and it's bright, right? So the days are bright and the nights are pretty dark, and then it's it's not well lit as in daytime. So, but then we also know that there are roughly, we can also see that there are around 2000 stars that are there in the night sky. So we can also see like many stars, many constellations as such during the night time. But our galaxy itself like contains billions and trillions of stars. So why not from the starlight? Okay, we can understand during the daytime that like sun is pretty close to us and it's very luminous with respect to our position in the solar system. So we can agree to the fact that we cannot see the starlight that is coming from various sources in the galaxy. But during the night time, when there is no sun, there is no sunlight that's being received in a specific area, or during the night time in that area. So why is the sky still so dark despite having billions and trillions of stars in our own galaxy? So this was the kind of a thought that actually Albert had, and this was actually also thought about by an astronomer called Thomas Hertz or someone. So he actually thought about it in the 16th century itself. So, but then this Henry Colbert, due to the advancement in the field of astronomy, he was able to observe and come to a proper conclusion about our universe as such through this thought experiment. Through this idea. So we know that the flux from the received by Earth from the star is given by F F is a flux, so it's a function of R as given by L by 4 pi R square. So we can calculate where L is the luminosity of the specific star. So the intensity of the coming light is given like the dj by j is nothing but your intensity. So dj by dr is nothing but L by 4 pi R square into n into R square. So n excuse me. So n into R square is nothing but the R square is again the distance. So for the intensity we multiply it again with the area, and we get the expression L by 4 pi. So to get the intensity from the above expression, we integrate it with respect to R. So when we integrate with respect to R, since we consider that the star is at an infinite distance or the source is at an infinite distance, we consider the integral to be from 0 to infinity. So when we integrate, NL by 4 pi is a constant, so it will come out. And then when we integrate, we get an observed result which tells us that the intensity of the incoming light is infinity. That means it should be always bright during the night and it shouldn't be dark at all. So this was kind of an absurd calculation slash observation that was made by Albert. So they had thought like what had gone wrong in the calculation or what they had assumed to be wrong. So let's look at the assumptions that were made based on the above results. So these are the assumptions that were made when they did the calculation, and they listed out the assumptions, and then to see when each assumption is put into scrutiny, which one doesn't hold up or which one fails to pass the specific criteria. So what first assumption that they did in this while calculating the intensity from a specific star is that the light that is being emitted from the star and being received by the Earth is unobstructed by anything else in the universe, and it just like straight comes from the star to the Earth. So the first assumption is that but we already know that the universe is not empty, and we have many objects that are present in between the star and the Earth. So that was the first assumption. But this could also this could also be true is because when the light emitted from the star is incident towards an object that is in between the Earth and the star, in between the path of the light, the object that absorbs it also reaches to the same surface temperature of the star, because energy, right, light energy is being transferred from the star to the specific object. So when it starts from the perspective of an observer that is watching it through on Earth, we see that the light that is being absorbed by the object that is in between the star and the Earth will also reach to the same almost equivalent surface temperature of the star. So that in order will pass on, and that can also that will not that can also give us the same flux density that is being received from the star to the Earth. So this assumption holds true to scrutiny. So we'll move on to the next one. The second assumption is that the number density n and the mean luminosity of L of stars are constant through the universe. So we also know that the number density is nothing but the kind of the density of the medium through which the light is traveling, right? To reach from the star to the Earth. And then the mean luminosity of the star is also constant. But for a fact, excuse me, I'll just get some water. My throat. Just excuse me for 1 minute. All right, guys. I'll continue with where I left off. 1 second. So the second assumption, yeah, exactly. So we say that the product NL is constant throughout the universe. So, but we know the N and L of R, what we found in the previous equation, was a function of radius. So it is not constant throughout the universe, but let's take for an example that there are many other stars that are at various distances and at various luminosities, right? So say that we are measuring a star that is around like 2 light years, and then there is another star in vicinity that's around like 1 light year. We can say that the star that is at 1 light year has has more luminosity than the star at 2 light years. But so what we'll receive is will not be able to see the star that is being that is at 2 light years away from us, but we'll able to receive the light better from the star that's 1 light year from us. So at that scale, we won't be able to receive the light from the star that's at 2 light years. So that portion of the sky, night sky, will be empty, and we will see only like a black spot right there. So to better your understanding, okay, 2 light years in the small scale. So like so let's consider like exactly what we use it at the daytime, right? So since sun has a great has a higher luminosity compared to like Sirius compared to on Earth, right? So that's why during the daytime we won't be able to see the stars such as Sirius as such. But during the night time, we don't see the sun, and then we see the Sirius. So the rest portion of the night remains dark, right? But then we can only see Sirius. So the amount of luminosity is not constant throughout the universe. So that is one of the reason exactly why we can see the night being dark, and then can only receive the light that is has more luminosity and is not that far from the Earth. So it will actually, and then in the third assumption, we assume that the universe is infinitely large. So if this was true, it could mean that like if say like the universe is so if the universe has a ever expanding radius such as r tends to infinity, so it excuse me. So say such as so let's say the maximum distance of the universe is at r, and then the total intensity that is received from the star that is present at the maximum distance is f of r. Sorry, in this case, the intensity. So, but then like this could also be a possible idea that can be regarded that can be regarded as a fault in this calculation, but it could also be that the universe can be infinite, but then the star that was formed was was made at a specific time. So it could what I'm trying to say is the star could have formed say at like say at like 2 million years ago, but then the universe is infinite, but then still the star formed 2 million years ago, so we'll still receive the light from the star, right? So this experiment due to this idea also cannot explain means can explain why the sky is dark. Sorry. And then the fourth assumption is that the universe is infinitely old. So in this assumption, obviously we can say that So if the universe is infinitely old, then that means this might not be true, because since the speed of light is finite, right? What we can say from the theory of relativity. So the speed of light is finite. So so say that we have a galaxy M31, and then we have an M31, that's Andromeda galaxy, uh, that's a specific light year away from us, and then we have say there's a star like 4 light years away, and there's another. So we'll receive the light from the star at 4 years after it is being emitted from the specific star. So due to that gap, we can also say that this does not actually if the universe has finite age, so the intensity that can be observed from the specific equation will be uh, NL R by 4 pi, right? So in this case of R, we'll substitute C times T naught. T naught is the like the infinite age of the universe, and then C is the light that is being speed of light from the specific from the specific star. So if we substitute that, this result will also be found if the universe is infinitely old. So that's what we say, that we can also vouch for this specific this thing as saying that if the universe is also infinitely old, we'll still receive the light from the star. But okay, uh, infinite it is still right, yeah. But then the universe would have contained the star only for a finite time. So the fourth assumption, it might be wrong because in the consider of calculation. So as to why we got the value of infinity. And the fifth assumption is that the flux of light from a distant source is given by the inverse square law of equation. So this was actually can be true because this cannot be true because if we consider 4 pi the inverse square law, which is based on the Euclidean geometry of the universe. So Euclidean space of the universe. But then, like in the later ages, Einstein came up and he told that there in our universe there the Euclidean geometry will not be applicable because the speed of light has a specific speed, and then we have due to gravitation and stuff. So the inverse square law actually was not used in this specific case. So from what we can say is that the assumption of the universe being infinitely large and then the universe being infinitely low does not hold up to scrutiny. So what we can say is that if the universe was infinitely old and then it was infinitely large, so we'd have to say that the light coming from the source had to be at a finite distance, right? So what if the light that is coming from the star is like it's out of our reach? It means to say that the light from the star will never reach us. So that is called as the universe horizon for our, like the horizon for our observation purposes. That's such that the light from that star can never reach us, and it would take light like infinite years to reach our sky. So this is one of the observation that was also made in order to say that the universe cannot be infinite and cannot be infinitely old. If that was the case, then there are some events that will never be seen it will never be seen even like after throughout our existence. So that is from these assumptions we can come to that conclusion, and this is actually a famous quote from a poet called Edgar Allan Poe. And then in one of his books, I guess it was explained in this case. So let the succession of star endless, then the background of the sky would be present as an uniform density. This is in the case that NL would is finite. I mean it is constant. Since there could be absolutely no point in all that background at which would not exist a star. Therefore, the only mode in which under such a state of affairs we would comprehend the voids which our telescopes find in innumerable directions would be supposing that the distance is so immense that no light ray from it has been able to reach us at all. So this is exactly the point in saying that the universe, if it was infinitely old and infinitely large, then the light from the specific star cannot reach us for like even if it takes a million or a billion years, because it is so far away, and with light due to having like only a finite speed would take a lot of time to reach us. So say, and if it's like 500 or 600 light years, say the star is 500 light years away. So if the star is emitting light right now, we'll be able to only observe the light after 500 or 600 years. So the concept of universe being infinitely large and infinitely known does not hold true. So this is one of the assumptions, one of the thoughts that I was able to actually, we were able to come to a basic idea that the universe is not infinitely and is not infinitely old. So any doubts? I know like I sped through the assumptions a little fast. So did any of you guys like like find any of this part like not able to you were not able to understand, or you need more insight into any of the assumptions? You can ask. Right. Guys? Hello. Yeah. So yeah. Which one? The flux one. Awesome. Like so flux is nothing but the amount of, so like generally in the as you define a flux of anything, say for like a flux of energy, right? So it is basically a measure of how much energy that is being received through a specific area, right? So we consider exactly like the star to be exactly spherical. So that is one assumption that we have for calculating the flux of this, the flux of the specific star compared to Earth. So L is nothing but the luminosity. Luminosity is nothing but the light that is being what do you say? Light that is being centered by the star to the Earth, the amount of light. So when we say this as flux density. In this case, we mean that the luminosity of the star that is being, amount of light that is being sent, like that is being emitted by the star per area by area, so per unit area. But then, like in this case, we consider it to be a sphere, so we use its surface area, that is 4 pi r square of the sphere. So any doubts, guys? Any other clarifications or any point you guys can ask right now? Okay, if not, I'll go further on with the talk. And so another fundamental observation that was essential, and this is one of the most essential observations that we've made so far to understand more about the universe, is that cosmological principle, the cosmological principle. So we use this to generalize the whole, the nature of the universe in terms of how it is in different directions and how it behaves in a specific distance. So the cosmological principle is the notion that a spatial distribution of matter in the universe is homogeneous and isotropic when viewed. Okay, this should be actually, I should have put in quotes because it's so important. The point that when viewed on a large enough scale. So to understand this, first we'll look at what is isotropy. So isotropy is nothing but the property of anything or a property of a space that can, it's indistinguishable whether you from like from where you look. So it is irrespective of the direction of the observer. So if I say, if you have your room that is completely empty, and then if you're standing in the middle, and then if you look at any direction, you're going to see the same white wall with the same everything. So you could say that the room is quite isotropic, considering that it has the exact same dimensions and exact same characteristics at all points, at all directions. So one such example is, say you have your navel. So that's one example of like they used to specify the distance. So say you're dropping a ball from at the height of a navel to the ground. So at this distance, say you're an average person is like so say this is 3 feet, right? So if I want to observe the ball from that point, it would obviously not be true because at such a small distance, we'll be able to identify the differences that are there in each direction, right? So this distance we can say. So my left is having a different thing. My left say so the left there is a guy here, and the right there is nothing. So the isotropy part does not hold true if considered in the if you consider it from the perspective of the ball that is being dropped at this height. So you can see the person that is being there, and then you can see various objects around you that is not the same in any case or in all directions. So the universe is not isotropic at this distance. So let's consider at a larger scale. So you have the earth and the sun, right? And then you have a whole sphere that is containing the earth and the sun. So this whole distance is 3 astronomical units. That means it is 3 times the distance from the earth to sun. The whole sphere of 3 astronomical units, the radius of the sphere is 3 astronomical units. So if you were to observe from any point in this sphere, so you can obviously make out a difference in a point where the sun, because the sun is very bright and is very luminous compared to other stars in this space. So we can obviously make out that the sun is in a specific direction and the other direction does not have the light that. So in this scale also we can also identify the difference in the directions based on the light that is being emitted at a specific point. So we can say that this amount of space is also not ideal to prove that the universe is isotropic. So let's consider an even bigger scale, that is 3 megaparsecs, 3 into 10 to the power 6 parsecond. So mind you, parsecond is also like very huge distance. So in this case you have, I'll say if you have like 2 galaxies in this sphere. Say let's consider the sphere of influence. So sphere under observation. Okay, so in this we have 2 galaxies, that is R1 galaxy, that is the Milky Way, and M31 is the Andromeda galaxy, our neighboring galaxy. So when we observe from a point in the galaxy, we'll be able to obviously make out that in this direction we can observe the Andromeda galaxy, but and then if we go to the other side in this direction, we'll obviously not be able to see. So we can also identify the direction based on the position of the Andromeda galaxy and say that I see the Andromeda galaxy from this side, but then on the other side it's not. So I can specify the direction that is peculiar only to the Andromeda galaxy. So even at this scale, we can say that the universe is not isotropic. So let's consider an even bigger scale. This is over 200 megaparseconds. So at this scale, we can see what is called as supergalactic clusters. So we have like cluster of galaxies on this side, we have another cluster of galaxies on this side, and then we have like galaxies everywhere, and then the light coming from the galaxies will also it will not make much, you cannot observe much of a difference in the light on this scale. So over 200 megaparsecs the distance, that is around, in case of I think it's around 20 into the power 20s, the radius of the sphere that we're considering here. So in this scale we can say that the universe is actually isotropic. So in meaning that at any point I look, it's gonna look almost the same due to the galaxy cluster that is being present almost everywhere around you, and then the light almost is identical at this point, at this scale. So if we go over 200 megaparsecond, distance, and because obviously our universe is way bigger than that, so we can almost, if you are going to measure at that scale, you can come to a conclusion that the universe is actually isotropic at this specific scale. So this is what isotropic is. Isotropy is nothing but at any direction if you go and then you observe, you shouldn't be able to notice any change in all of the directions. So in this case, as in this case, in this very short distance, you'll be able to tell the difference between the directions. And even in this case, because you can observe the light from the sun in one direction, so you will be able to tell the direction in terms of the sunlight with respect to sun. And then in this case, you can tell with respect to the Andromeda galaxy at this scale. But in this scale, you have galaxies everywhere, and then you have super clusters, which will, it's a cluster of galaxies on this side and the cluster of galaxies on this side and everywhere. So we can almost not tell the difference between in the directions at this huge enough scale. And then at this point, we can consider this part of the universe is isotropic. I mean, the universe is isotropic. So, and we consider to homogeneity. Homogeneity is nothing but the consistency in the stuff that is present in the universe. So, like I can't have a planet, say a star of some say like 3 10 to the 6 meter radius, kilometer radius, and then I can't have another star in the neighboring part of the universe that has like 6 or 7 into 10 to the 6 meter radius. So that defeats the whole purpose of homogeneity. Homogeneity means like uniformity in the whole universe. So one example that we can use to understand the difference between homogeneity and isotropy is that in this stripes, we can say that the black stripes are homogeneous in the homogeneous in the figure. As you can also tell the direction at which the black stripes are going based on based on the this thing. The white stripes, you can say the white stripes is also. So we can say the black stripes are homogeneous. In this case, they are of the same length and they are of the thickness in almost all the directions. So this is an example of a substance that is homogeneous but not isotropic. Because you can see if you are standing on the black strand and then you can see the white strand next to it. So you can obviously tell the difference between like the black stripe and the white stripe, right? Like based on where you're standing. So this figure is an example of a homogeneous type system rather than an isotropic type system. So this is a homogeneous system and a non-isotropic, anisotropic system. So let's go to the second case. So in this case, we can see this is isotropic. If you're standing on the circle, we can see that there are circles around us everywhere. But this is not homogeneous because you have circles of different radius around this. I mean in the figure. So this is an example of a thing which is isotropic but is non-homogeneous. So, but to consider the cosmos at a very great scale, that is over 200 megaparsec distance, we say that the universe is around a spatial distribution. That is, you have all the stuff around you. In the case like, so we have supergalactic clusters as such. You can say that the universe at a scale that is large enough to not identify any differences at all the directions, and is quite evenly distributed with the matter that can call the universe, since the universe is of much bigger scale than example, we can say that the universe is homogeneous and isotropic. So this is the basic fundamental cosmological principle that we use in order to understand more about the universe. So you have any doubts, any clarifications on this point, or you need anything more that needs to be added to make you understand better, you can ask. If not, I can move to the next thing. So just remember that what I mean by the in the scale, as in say your size of the room or size of your house or size of the, this is in a very very scale wherein the objects as such look all similar, and then you cannot tell the difference between the different directions in the objects that are present in various directions in the universe. You feel they are all homogeneous and isotropic. So at that scale, we can consider the universe to be homogeneous and isotropic. So that's what the statement means. If you right, I'll move on to the next one. And one second, let me see what time it is. Okay, we have 4:45. Okay, so we know that as distance increase, as the relative distance increases between the source or the observer and the source, or vice versa, we can observe there is a shift in the wavelength of the light that is being emitted by the source. So this is what we commonly studied as the Doppler effect, or the Doppler shift in the wavelength of light. So we have two kinds of shifts in this. One is if the source is moving towards the observer, we can say that the light emitted from the object, from the source, is blue shifted in comparison to the observer. That means that the apparent wavelength of the light decreases as the relative distance between the source and the observer decreases. And the other case is that we find that the light that is being emitted by uh, tends to be redshifted if the source is moving away from the observer. So this is also can be explained with the is a basic formula. Z is the amount of redshift that the light that the amount of redshifted light that is being observed. So this is the wavelength of the observed by the observer due to the from the source, minus the wavelength of the light that is being emitted by the source, divided by the wavelength of the light emitted by the source. So this actually this has no unit. It's just only a measure of through what factor the wavelength of the light has increased or decreased as with the relative distance between the source and observer, like changing with time. So we also know that the common idea that the proved thing such that the universe is constantly expanding. That means the objects in the universe are moving away from each other. But understand this carefully. This is not due to the due to the rotation or the movement of the objects in the as such. This is because of the expansion of the space on which the objects are. Like the space time we have, it's constantly expanding. This is not due to the motion of the objects as such. So what we usually find is that the light from many galaxies, when we observe, it is mostly in most cases we find it to be redshifted. So this we can use the value of the redshift to identify the distance of the source from the observer. Like we can use it to find the distance of galaxies and superclusters as etc. So Hubble is the one who actually was able to calculate by how much exactly is the universe accelerating. That's also called like how much is that's the recessional velocity it's called as. So the Hubble's reformulation of the Doppler effect, that is also called as cosmological redshift, is given by Z is equals to h naught by c into d. So here h naught is the Hubble's constant, and then c is the speed of light, and d is the distance between the source and the observer. So this is a basic graph which we can use, which is being plotted through the light that is being emitted by the star, and then light that's being emitted by the star is given here, and then the distance, and then the velocity at which the object is moving away from us. So we can use the amount of redshift that is being observed with the to understand how far with what velocity the object is moving away or towards the source, towards the observer, and we can also calculate the amount of redshift that we get. So but once yeah so under non if one second. So, do you guys have any doubts still here? Like, is there anything that you need more clarification with, as such? So, you guys, like, I take it that you guys have like followed me, like followed what I was speaking till now. I mean, some of this could actually be like common for you guys to understand since you guys have already learned it in your previous semesters. But yeah, so okay, and I'll continue with this. Why we can, since the redshift, usually what we observe from light incident from the source is basically like in the factor of 0.0. So this formula actually gives us the amount of redshift. So we calculate that the amount of redshift is 0.04 what we observe. So under this case, we can tell that the light, like we can consider in such a distance that under non-relativistic conditions, because the value of redshift is very less. So we can consider the whole system to be in an non-relativistic condition, and we can take the z to be a factor of the speed of the object moving, and then the speed of light. Since the object is moving at a very less speed compared to the speed of light, we can consider this whole case to be a non-relativistic case, and we can apply our normal classical mechanics, classical laws into this formula. So we have z is equals to v by c. So, but we know our sorry, we have our v is equals velocity is equals to h naught times r. So when we substitute this, when we substitute the value of a v in this case, we can actually find the value of the Hubble's constant, since we already know the value of z in this case. So if you substitute your v in the place of z, we substitute v by c, we can get the value of h naught in this case, knowing the distance on a notion that we know the distance between the two objects. So what Hubble first calculated was that the distance, I mean the space itself is accelerating at 500 kilometers per second per megaparsec. So this formula, I mean this value actually was found to be incorrect, as Hubble, like he way underestimated the cosmological distance as such way too much, and he didn't actually consider various factors such as the gravitational force, and then he didn't consider other factors, and he greatly underestimated the distances that the cosmos can have. So later he reformulated the other factors, and he was able to come up with a conclusion that the universe is accelerating at 70 plus or minus, because we cannot know for sure the whole the distance as such due to the constraints of how much we can observe in the universe. So we have 70 plus or minus 7 kilometers per second per megaparsec. So the Hubble's constant gives us the velocity or the rate at which the universe is expanding each second. So it is expanding at this speed, is what we can say. And in the same case, we can use the okay. So before this, like, did you guys like understand what the whole concept was? Can I get some responses, guys? Yeah. Okay. So the next is the Hubble time. Hubble time, calculated by r by v, that is time. So you have the distance between the source and the observer divided by the velocity at which the source is moving away or towards the observer, or vice versa. So we calculated the value, I mean the expression that v is equals to h naught times r. So when we substitute it in this relation, we can get that t is equals to h naught inverse. So the value what we found out for Hubble's constant was 70 plus or minus 7 kilometers per second per megaparsec. So when we substitute the value here, we can actually calculate the expansion in space that has occurred since the two bodies were, towards, I mean, were together, like in contact with each other. So that is that is obviously a theoretical thing, because this has something to do with the whole concept of inflation and the whole concept of Big Bang theory, saying that the all of universe was just at a single point and until it all just expand, went into a enormous expansion, and this is what created all of matter and all of things around us, all from a single point. So the Hubble's time is what gives us the time period, the time, the time elapsed when since the two galaxies or any two bodies were in contact with each other. So when we take the reciprocal of this value, we get the value that is 14.0 plus or minus 1.4 giga years. So giga years is equivalent to a billion. Giga is equivalent to a billion. So it is almost close. We know that the universe is 0.8 billion years. So if we take 14 minus 1.4, 30, I mean 12.8, and then if you add, you can get a close, like a very close value to the age of the universe as such. So we can also say that the theory of the Hubble's theory of cosmic expansion is also true, and then it is also accurate. And then this is the whole, we can find the age of the universe in this method also. And the Hubble's distance. So remember what I talked during the fundamental observation concept of the light that can never reach us, since it's at a distance way way far, such that the light can never reach us, or photon to us, no matter how many years, million years it takes. So the Hubble's distance is exactly the distance. So basically, our whole sphere is. I wish I could draw something in order to show. So our whole universe of that can be observed by us is given to a sphere, and then that sphere has a diameter of 4300 plus or minus 400 megaparsec. So whatever happens at a distance greater than this will never be observed by us, or the light from that particular object that is at a greater distance than this distance will never be observed to us. The photon doesn't reach to us, since it takes a lot of time, and through the gradual expansion of the universe, it will never reach us. So this formula is like distance is equals to velocity. Velocity by time. So time is h naught inverse. So we can distance velocity into time, and then we found out the Hubble time to be h naught inverse. So C by h naught will give us the value, and this value is exactly will tell us like how, up to what extent the universe can be observable at one particular point in the universe. So this is a very important and interesting concept, and this is also what one of the reasons for like people have been suspecting like the dark energy and then dark matter to be there. So dark energy to be there. So because a gravitational force is basically since there is also gravitation, so why are the objects moving away from each other? So this is one of the explanations that can be done, and this calculated values are all. We cannot see over the distance. We cannot observe anything at a greater distance than the specified distance. So yeah, another concept, since we've gotten to the idea that the universe is constantly expanding. So one of the theories that came up was steady state universe, which was actually given by. Let me check 1 second. Yeah, so it was given by Hermann Bondi, Thomas Gold, and Fred Hoyle. So they were the people who got the who got at the concept of a steady state universe. So what is a steady state universe? A steady state universe is like a model in which the universe is the density of the universe is always constant. So when we consider that, obviously the matter is inside is there, and then all of space is expanding gradually as time goes on. So that in order to keep the density of the universe constant, there has to be constant evolution of matter. In order to fix the value of density, that has to be a constant. But we also this also violates the mass energy principle, such that mass cannot be created or destroyed, and that is one of the cases that people actually went with the Big Bang theory rather than the steady state universe theory. So the steady state universe, the justification can be given as the velocity at such a recessional velocity, or sorry, velocity at which the bodies move away from each other is given by dr by dt equals to h naught times r. So when we integrate it with respect to in terms of r, we can get the expression r of t, because we don't consider excuse me, we don't consider the object's motion to be the exact reason, object's position to be exact reason, a reference point for the expansion of the universe. It only the expansion of the universe only depends on the time, depends on time. So we have r as a function of time is proportional to e times e to the power h naught t. So we know the volume if we consider, that's what I meant, right? Like the sphere is what I meant. So whatever happens outside the sphere can never reach us, can never be observed by by an observer inside the sphere. So we consider the volume, that is 4 pi r cube by 3, is proportional also to e to the power 3 times h naught t. So this is a volume of what Hubble had given. Given an idea of. This is so. In order to consider the mass, that is, like how the mass is being compensated, as the density always has to remain constant despite the expansion of the universe, right? As volume is keep increasing gradually. So we have m as a steady state is equals to rho naught times v. So here rho naught is the density that is always a constant, right? So the density times the volume. So density times the volume, that is 3 times h naught v. Okay. So the density of the steady state universe will be mss by v, that is 3 times h naught times rho naught, that is 6, because the current density of the universe is around 3 into 10 to the power minus 27 kilograms per meter cube per giga year. Per kilogram per meter cube, sorry, giga is considering the scale factor and Hubble's constant. So we have the value that the actual steady state volume of the universe has, but obviously this was found to be wrong because like we can't create matter out of anything and then expect it to do behave that way just in order to like make a theory work. So this idea was disregarded, and people started to go behind the Big Bang theory, as since it gave a better explanation in comparison to the steady state universe, and also assumes that the universe and it has been expanding ever since. So I think time is up. So yeah, I think I'll wrap up with this point. If you guys have any doubts or any clarifications, you are free to ask right now. So